Thank you very much for inviting me. Yeah. It's a pleasure to be here, to be back here. What I will present to you is joint work with Carsten Bormann, who's my PhD student, and Julia Schaumburg, who was a former PhD student, who's now assistant prof at Vrije University in Amsterdam. So I want to talk with you extremal dependence. And the question we are asking is fairly simple. It's just a fact, when you have extremal dependence, is it enough to just look at bivariate dependence, or do you need more? And when do you need more? And what is the impact if a test tells you that you need more? Yeah? So the question is fairly simple, but we want to develop a formal test for this, and not just a formal test. If we find significance by that test, we also want to go further and assess what does it mean in terms of risk level, in terms of impact. Okay, so that's the plan. So why would you be interested in something like that? Why worry about dimension 2 and beyond? If you look at extreme risks and dependence of extreme risks, if you look at the theoretical literature which is there, and also in particular at the applied literature, you find that what is done there is, in the applied literature, exclusively looking on bivariate dependence only. Nobody worries about multivariate dependence in the extremes. The reason for that is mostly computational tractability. Yeah? So people say there's not a lot of data. If we work in the extremes, it's even less. And then if we go multivariate, then it's even less. So we can't do anything. Yeah? So that's the usual argument why things stay bivariate. Also from the theoretical side, there's some arguments why this is actually so far the standard in the literature. If you look at tail copulas, then also from the theory side, the theory is just well developed for bivariate models. If you want to go multivariate, then you face problems if you want to stay non-parametric. You face problems that you have to decide if your model should be one which allows for asymptotic independence or which allows for asymptotic dependence. So you have to decide up front, but it's something which you want to learn from the data. Yeah? So there's also from the theoretical side reasons why the literature has stayed bivariate. Yeah? So on the other hand, if you look at the recent financial crisis or crisis situations in general, we have seen that it might not be enough to just look at bivariate dependence. In crisis situations, we have witnessed lately that we gain in complexity of the financial system, meaning that the dependence structure in the system is not just bivariate, but it becomes highly complex and multivariate. Yeah? And in fact, these effects seem to be the main drivers of risk in such a crisis situation. So it seems that this part is not something you should ignore, in particular in crisis times. So it seems to be something you should worry about, or at least you should ask the question, is it there? Is it significant? And what does it matter? In which way? Yeah? So what we find, and so that's already kind of hinting to where we're getting, is if you ignore these higher order dependencies, the dependencies beyond level 2, this can lead to a severe underestimation of the true risk levels. And if you underestimate, then you don't know what you're doing, really. So this can, if a lot of people proceed in that way, this can pose a threat to the stability of the financial system. So it seems to be sort of relevant. Yeah? So what we do here is we propose a formal statistical test to detect when these higher order tail dependence beyond dimension 2, which we call HOD, has a significant impact. So that's step 1, and then in the application I will show you how we assess if such situations really matter, in which way they matter. Yeah? So what we think we contribute is the following. So we developed this test. It's a non-parametric test, so we don't rely on any sort of form assumption. So there's no debate if we have chosen the right functional form of the correct copula and if you should have chosen another one and it would have gotten another result. So it's fully non-parametric. And so we test if there exists a relevant higher dimensional cross-sectional tail risk, yeah, in the cross-section. And it's not just that we derived the test, we also developed the asymptotic properties, so we developed the size and the power. And what we find here is that that's not enough. If you want to apply the procedure, you have to have a bootstrap version because of the scarcity of data on the one hand, and also if you look at the variance, I will point to this, it's not possible to directly implement that for the cases we are interested in. There's no closed form, so there's a real need for the bootstrap. It's not just an add-on, it's essential here. And then what we do is we conduct a simulation study, which we think is quite thorough now, and where we study the finite sample behavior of our test. And we do this in particular in financial time series settings. So if you look at the literature of extremes or extreme risks, you find that people just look at IID data mostly because the whole theory is developed in this framework. When people apply it to finance, they just ignore it away, yeah? So they don't bother. And the question is, what is the impact if you have a time series, and that's what we study there, yeah? So if you pre-filter, if you don't pre-filter, if we take the wrong pre-filter, what happens? Does it matter? Yeah, it does, yeah, we'll find the results. So we study this. And then we apply our test to the following setting. So what we think of here is a setting of international finance. So it's not like large portfolios, because there it's clear that higher order dependencies matter if you have thousands of stocks. Yeah? So we are talking about higher dimensional settings, so meaning settings of, I don't know, dimension up to 10, where you can really ask, does the dimension beyond 2 matter or not? Yeah? So what we look at is international stock market indices. And we detect a significant increase in multivariate extreme risk during this 2007 crisis, which can be mainly attributed to these HOTS. So in other words, if you just look at the bivariate dependence structure, there is no time variation at all. It stays constant. And so we find that apparently the whole time variation comes from these higher order effects, and these increase drastically. And then on top, we quantify the impact of disregarding these HOTS, although they should be there. Yeah? So you could say, well, it's statistically significant, but I don't care. Like, maybe it's just a mild effect. And by assessing just a small portfolio and check what does it mean for the risk level of the portfolio, how wrong am I if I just ignore that? And we find it matters a lot, up to 50%. Yeah, so it's not something you should ignore. Okay, so now let's talk details. So here comes the test idea. So as I told you, we talk extremes, so we have to work with some of these concepts from extreme value theory. And what we do here is we decide to use the concept of a stable tail dependence function. It's sort of in contrast to a copula. So you might know a copula for the full distribution. So you can also define a copula for the tails. Yeah? But we are not working with a copula. Instead, we use a stable tail dependence function which connects the univariate margins. It connects them in the following way. This L thing is defined as whenever one of these marginal extremes exceeds its univariate quantile, its univariate extreme quantile, then that's the event we are interested in. So it's enough that just one of this margin exceeds. For a copula, you would want that all of the margins exceed simultaneously. Yeah? So here, in a sense, this is a bit more conservative. Yeah? So for a copula, you want that everything is extreme, all dimensions are extreme in simultaneously. For us, it's enough that one of the dimensions is extreme. Yeah? So we are sort of conservative in the sense that we are alerted earlier, in a sense, yeah, when there's trouble in the air. So this L function is something like an asymptotic dependence probability, which is it's not a probability, it's something scaled. So it's not in the range between 0 and 1. It's in the range, if you look at this, between the maximum of this little xj and the sum of all xj's. Yeah? So it's a scaled asymptotic probability. And what we then do is then fairly straightforward. Yeah? So we decompose this stable tail dependence function thing into 3 parts. We decompose it into univariate part, so xj exceeds its univariate quanta, into the bivariate part, so you take all pairs. Yeah? So to decompose the L, now you have to subtract sort of the copula event of the bivariate thing, so it's alternating. Yeah? And then you have the remaining part, which is of higher order dependence. Yeah? So we have a univariate component, a bivariate, and something higher dimensional. Yeah? Here in the case of 3 dimensions, this is the only thing. In a higher dimensional case, this red thing would be larger. And so what we are interested in, formally now, is to check if this red part is significantly different from 0. Yeah? In the sample. Okay, so here's then the test. So we check if this delta, remember delta is this red thing, if delta is significantly different from 0. So delta we obtain as taking L and subtracting the blue and the yellow parts. Yeah? The blue part is easy, these probabilities is just, these are the univariate quantiles, so this is just little xj's. Yeah? And here we can calculate this easily by using that the intersection event is the probability of each event summed up, and then with the little L of the 2-dimensional thing. Yeah? If you sum up, then you have that this is 2 minus d of the sum of the xj's, and then you have the 2-dimensional little L, which appears. So this is our delta, and we want to check the null hypothesis. Is delta equal to 0? So that means there's no higher order dependencies. Or do we deviate significantly from this, meaning that this delta is larger than 0? So that meaning that there exist joint extremes of dimension larger or equal than 3. Well, then all we do now is we take sample analogs. So we take sample analogs of if we know how to estimate L, we can do it for the full multivariate thing, and we can do it for the 2-dimensional thing in the same way. Sample analog works as follows. So for the extremes, you use rank statistics. Yeah, so it's nothing to be scared of. We talk about extremes, so we want to take the most extreme observations. Yeah? So what we take is then we're interested in events when each marginal exceeds some order statistic, and so this is the n minus kth largest order statistic. Forget about the 0.5 here, and just take this as a 1. Yeah? Then this is the n minus k largest order statistic. So intuitively, that's something which sort of you would expect to happen. Yeah? We talk extremes, so we want to take the largest values. Yeah? So I can't take all of them, I have to cut off, and I cut off with k. Yeah? Then for each margin, I have k observations. So that means I take the sample average of the observations in here. Yeah? Okay, so this looks scary, but it's not really. So now if we can estimate L, we use the estimator in here, and we use it in here. We plug it in, and then we have an estimator for delta. Yeah? So the question is now how to proceed with delta, yeah? And to derive the asymptotics for that. That's not so easy anymore. Yeah? But if you work with it, then what we found is the following. For the size, we find that we have the following limit theorem. So the delta approaches the true delta at the speed root k. So if you have heard of non-parametric estimators, it's clear that sort of this k is a smoothing parameter which you have here, so cut off with k. It's clear that this k somehow triggers the speed of convergence. Yeah? And you end up with something normal if you're working hard enough. And what is interesting here now is the following, is the conditions which we need. We need that L exists, that's nothing to worry about. If this doesn't exist, then it's really, you can't do a lot. We need at least one bivariate pair which is tail dependent, otherwise it doesn't make sense actually to look at higher order dependencies. If you don't even have bivariate dependence, why then care, right? What do you do in practice? You test if there's bivariate dependence. Yeah? And then you have to worry about how to choose this k. Yeah? So asymptotically, this is what you do. So you have, this depends on a parameter beta, which is the degree of regular variation of this random vector thing. So what is this? So it's multivariate regular variation. So you have the distribution of this full dimensional x, and then it's all about the tails. How much is in the tails? How fast do they decay? If they decay slowly, then you have a lot of information in the tails. That means you can cut off quite sharply in the tails out in the tails. So your k can be larger. Yeah? And this is exactly what is reflected in here. Yeah? And well, what you need here is either the data has to be IID or the extremal index, which indicates the clustering of extremes, has to be nice. It has to be close to 1, so there shouldn't be too much clustering. Yeah? So that's a bit unrealistic when we want to work with time series and financial time series. What you could do then, if you deviate with the theta, you have to correct the sigma matrix here. That's the one thing, but it's hard in terms of estimation. Or what we do is pre-filtering. So we pre-filter the time series such that we end up with IID residuals or close to IID residuals. And then this variance thing can be calculated only under no extreme dependence. So that's not really the case we're interested in, right? And here is why we need the bootstrap. So we can't, there is no way to calculate this explicitly. You have to bootstrap this thing under the case of tail dependence. Yeah? So here's the implementation. As I promised, what we do is we pre-writen financial time series data.
Does that mean using a sieve, basically?
No, we just use gauge, any AMA, gauge, whatever. I'll show you. And then we look at the residuals, and we find that they fulfill this condition on the extremal index. So this is no clustering anymore, so we don't have to worry. Yeah? And then we use some subsampling procedure because it's optimal for extreme values to use subsampling. And what is described here, this bootstrap is straightforward. Yeah, you sample and then you create your bootstrap sample. From this, you have your statistic and you calculate the sample variance of this. And then it's a double bootstrap because you have to calculate for each bootstrap sample you create, you have to choose a new k. Yeah, so you choose k first, depending on the data, then you subsample, and then you continue. Yeah. So, but it's straightforward. Yeah.
Is there a specific bootstrap you have to use? Because you have to preserve the extremes, right?
This is done with the subsampling, so there's no. That's fine. Why should there be a problem?
Just with extreme data, often the bootstrap you use is very important, right? Otherwise you can lose the extremes, but yeah, I guess that's what we want.
No, that's correct. It's not something we calculated, it's existing results that you can do that. That's why you use the subsampling thing such that you don't lose that. Okay, so we simulate, as I promised, here we take care of the time series structure. We have two types of distributions which we look at. Use as this meta-T distribution and this max factor models. They seem a bit odd. Why to choose these? Here for this meta-T, you can control the univariate and the copular effect separately. This is why we don't use a multivariate T, but this meta-T where we have a handle on this dependence parameter separately from the univariate tail behavior. Yeah? And then this max factor models, there's the type of factor models you would use for extreme values. Yeah, so that's the analogon for the tail. It's a tail factor model. Yeah. Okay, and here in these type of models, we can control when we are under H0 and when we are under the alternative. Yeah, so we directly see what happens. Then, as I promised, so what we do is we use IID data, we use arch-gauge type time series filters before. And in the time series case, we consider no or pure AR, pure gauge, and correct pre-filtering and check what matters most. Yeah? And for the size, we find, so generally for size and power, we find if we correctly pre-filter, then there is no effect as you would expect, because you estimate non-parametrically the dependence structure, and if you pre-filter parametrically, you wouldn't expect any impact. Yeah, so this shouldn't matter, yeah, intuitively, and that's also what we find. Showing this formally is not possible. You would need some analysis of probability type of results for this rank order statistics, which are not available yet. Yeah, so that's not trivial to show that it doesn't matter. But in the simulations, it's possible. So we see it doesn't matter, and we see what matters in the time series is the gauge effect, as you would expect. Yeah, if you miss out on that, then you have a wrong impact on the test. Yeah? If you miss the gauge filter and it should be there, you find wrong results. You overestimate the impact of the higher order dependencies, as you would intuitively also hopefully think of. Okay, exemplary results. So if we have an unfiltered gauge process and we have this T marginal errors linked with a T copula, so this is meta T. If you increase the dependence and if you increase the dimensions, you would expect the power to rise. And here that's actually the setting where we go wrong. So we have a time series setting, but we don't pre-filter. Yeah, and then you see in the best case of 7 dimensions and a very strong dependent structure, the power can be up to 86%, which is not too bad, but in like a case of 3 dimensions and just a mild dependence, so not too far away from the 0, the power can be really bad. Yeah, so there is an impact. Yeah. Results look significantly much better than when you do the correct pre-filtering. So this is as bad as it can get. Right? Then for the application side, we look at the following setting. We look at stock return indices, and we look at 2 different types of settings. We look at a global portfolio, and we look at a European type portfolio. What we mean by global portfolio is just the US, then some Pacific index and a European index. We look at this on a weekly frequency to avoid time zone effects. And then we take a European portfolio where we have like the major European countries, 7 countries, and we look at this on a daily frequency because we don't have the time zone effects. We use rolling windows, and we apply the test bi-weekly and every 5 days in the European case. We use a time series pre-filtering of AMA type, gauge type, and AMA T gauge type to have asymmetry effects. Cope for. In the case of Europe, we also use a factor to control if the effects just are due to a common factor or not, and we find there is still something remaining. Yeah? Let's just have a brief look at the results. In the global portfolio, what is marked here is the time periods when you would reject TA0, they are marked in gray. So and you have the losses on the right and the gains on the losses on the left and the gains on the right. So you would see in the case of the global portfolio, you would only reject the bivariate case well after the crisis. So this is unfiltered. Maybe we look down here because it's more realistic. Yeah? Here only from after 2009 on. Yeah? So before it was okay, yeah, to actually do it. Yeah? Whereas in the European portfolio, it was never okay. So countries are more connected, as you would also expect. But what you see here is a very steep rise during the crisis, even when you filter for the time series. Yeah? And you see a rise in losses and in gains, and they look almost symmetric. So that's also new in the literature. When you just look at bivariate effects, people found that for the gains somehow look differently. If you look at the HOTS, they're sort of symmetric. Yeah? These results remain if we control for this common factor in Europe. Yeah, we use just a factor of the other world, yeah, some index. And in the losses it prevails, although it's a bit less. Yeah? So it goes down somehow. Yeah? But it's still something remains. So here, just quickly, the impact of this regarding the HOTS in the European portfolio, I will be quick on this. We look at an expected shortfall scenario where we compare to just the bivariate setting, and we look at the full setting. And then we compare the risk levels which are induced by the 2 types of models. And then you see in the case of Europe, this is the case we are more interested in because we find HOTS all the time. You see it's 60%, yeah, you only get. Yeah? Sometimes it's even less. Yeah? So that's really scary. Yeah? So here's the summary. So we propose this test. We have the asymptotics. We do finite sample studies, find that it works also there, and we look at an application where we find it has an impact. Thank you.
Thanks.